Well, I guess we'll go ahead and start so we can finish early. So the moving stuff. So if you have a moving body with a constant velocity, it's actually pretty simple. So if you stare at this, he's made this little red, the controlled volume. And then it's this vane or whatever this is, he's calling it B. Whatever that is, B is moving to the left. But the water is shooting, assuming it's water, shooting out at VF. Hopefully, to have a reasonable problem, VF needs to be larger to VB so it catches up to this thing and hits it and spews off down and up to the right. So if you're sitting on the object B, then you see the velocity coming in at the velocity of the fluid relative to B. And so all you're doing is, if it's coming at 10 meters per second and you're moving at 5, then it appears like it's hitting you at 5. And it's that simple. There's nothing more really to these. And actually, believe it or not, that's that's all he's written. That's it. Yeah. So let's see if I can find now. I'm sorry, I'm coughing up here. Okay, I think I touched that. Okay, let's look at his example. It has two examples. They're probably fairly simple. Oh, that's weird. Okay, a truck is moving to the left at 5 into a 50 millimeter diameter stream of water, which has a discharge of 8 liters per second. Determine the dynamic force of the stream exerted on the truck if it's deflected off the windshield in a vertical plane. So 40 degrees, 5 meters per second. So you're kind of doing a vector diagram. Okay, so I'll let him figure it. So there you go. There's Fx and there's Fy. And then you got to do, okay, so he's figuring out all this stuff. He figures out his Q. And then he says the velocity of the fluid with relative to A. Now, A is supposed to be, pretty sure A is the control volume thing there. Oh, man. And so it comes in, so it's shooting in at 4, it has a weird number, 4.074 meters per second, shooting out of the stream. The truck is coming at it. So relatively speaking, you add them together in the red, what's it called? The red control volume. So you see the 5 meters is heading to the left. This is heading to the right. So, you're right. So this is negative. This is positive. But the control volume is seeing this coming at 9, a little over 9. And so that's what he's got. Then, he's going to go through. Application of Boole would show the relative average speed and maintain the waterfall, neglect the effects of elevation. Okay, then he comes in and he does linear momentum. So he's going to tell us that this term is steady state and that we have two control parts of the control volume. The part where it's coming in and hitting you, and then the part that's shooting out. I basically described those in reverse. So in other words, like so. Okay. Hey, you know what? I think I've got one more page, and then what I'm gonna do is just do a copy, and then I'll do a paste, do a bunch of paste, and go back to right there. So I used to know the command key to do that, but I don't know that I know that. Yeah, I was thinking of just clipping a part of it though. Just so if you look at it from that perspective, it's kind of weird. Well, I guess it would look better if I did it that way. So what's funny is from the guy sitting in the truck, it appears to be going out like that, but the truck is moving to the left at 5. So it's kind of like the velocity of the fluid is equal to the velocity of the fluid relative to the truck plus the velocity of the truck. So this fluid relative to the truck is going to be one thing, and then the VB is going to be the -5. So let's see how he handles that. Oh, man. I probably should have copied all that. So what's interesting, so he says the velocity of the fluid relative to B times the cosine of 40. Well, that's because it's 40 degrees. Oh, man. And then, so this is the component of the velocity, and this is the kind of the m dot, 1,000 kilograms per meter squared. There's your 9 point whatever. The area. Okay, so he's assuming it's a circular, like the jet is 0.025 meters in radius. Like, what do you mean? This part or? Oh, okay, yeah. Oh, 0.5. Okay. Yeah. Now, did he put 0.25 in there? Oh, yeah. Okay. Yeah. So that's your radius right there. Radius squared pi. Radius squared pi. He's assuming that the radius doesn't change. That's reasonable. You got to assume that, even though you know if the water hit it, it's going to spew off of it a little bit. And so he gets f of x, and then he goes through and gets f of y. The thing about f of y is the only component that creates the y is the exit at the top of the truck. And that's pretty much it. So all you're doing with these is you're just subtracting. Oh, well, wait a minute. That's not the same problem. Okay. So then, usually, people don't cover this section, but since he has done this in the correct way, I think I'll go ahead and cover it. Although I'm not sure I'm going to give a problem because the problems are so long. If I did, I mean, I don't know. So the water spews in and hits something that's rotating. Now, that's not a good, okay. So he goes through and finds the angular. What you find out is R cross MV. So inside Reynolds equation, you get this. So this is actually sum of the torques. This is the torque on the left-hand side. And then usually the time-dependent term isn't considered. And then you get this term, which is R cross V. But you got to have this V being the actual velocity exit. So more times than not, this local angular change about this time-dependent term is going to be 0. So there he's got it steady flow. So the R cross V, the key here is So we've got, oh, okay. Well, that section was pretty short too. I expected that to be longer. Let's look at an example. Okay, that's not a good example. There's no rotating equipment there. Okay, so here's rotating equipment. So the key here is for the R cross V, you got to have the velocity of the fluid relative to, a person sitting still. So you're sitting here staring at this, and you're seeing this spin, and you're seeing the water come off at an angle, which is different than if you were on the object itself. And I think this 2 points are the key.
Is that like, on one of the carnival rides or whatever, you put a ball of water and open it? The way you look at how it comes out is different than if you just stand on the outside.
That's correct. Yeah, exactly. Because what a person might see. So you'd be on the merry-go-round, right? And let's say you squirted it straight out. So you would see it going straight out. But the person who saw this, let's say this thing is spinning pretty fast. So he would see a component of the water spewing out like that too. So essentially it's that equation that was related back in dynamics. The velocity of the fluid is equal to, and actually this should be a velocity of the fluid, related to the person on the merry-go-round. I call it P, plus the velocity of the person on the merry-go-round. Person on the merry-go-round is going to experience omega cross R. So he's going to be sitting there, but the person on the merry-go-round sees that velocity. So maybe he sees a velocity straight out. So if you look at it from polar coordinates, just put the guy on the merry-go-round right there. So he would see the velocity of the fluid relative here may be something like, let's just say 10 E. I wonder if he's got to use UR, where UR is this direction and U theta is that direction. So here, let's say the omega is spinning. Let's see, omega is say 10 and R is equal to 10. So what this person here would see is 10 times 10 U theta plus the 10 here. So this is what a person sitting out on the ground would see. Would see the water spewing out directly out, but it would also, because as the particles came out, kind of like this, through time, you might see a particle come out here. How could I do that? So it'd be kind of like the water would be spewing out kind of like that. Does that make sense? Or actually, no. Say, if you trace the particle, the person, so back here, they spewed the particle out. It would be out here at that point, here and here. So they would see this. The person standing out here looking at the merry-go-round. You'd see the spray coming out like that. So actually, if you zoom in on it, they're going to see a velocity coming out like that. So that's where you add these things together. You got the spin rate, which I made this thing spin really fast. And then you got the shootout rate. Now, thing about this is that's if you are shooting it directly out. So if you're sitting there and you're on the merry-go-round, you shoot it directly out. But what would happen if you shooted it back? This could have a UR component and a U theta component. This will only ever have a U theta component because, the person's sitting there spinning around and around. So if you look back at this thing, that's kind of what he's doing. So he starts with VA is equal to omega R, 100, 2 pi, 1. So he gets 3.141 meters per second squared. That is what's shooting out. So therefore, the tangential exit velocity of the water from each nozzle through the opening control surface, looking down the fixed control figure. What does that figure look like? Oh, that's that. Okay, so he has made the water bottle squirt directly tangent to the path. So what he's done is he's made it directly squirt tangent here. He has no UR component. He only has this component. So he can add them directly together. And so you get in there and you add it directly together and you'll see the velocity of the fluid shooting out from the observer that's standing out on the ground, sees it at 1.633 meters per second. And then you're just going in and putting all this in and you're getting the moment that's required. Now, let's find one that has angles to it. There has to be the use of somebody like that. Maybe this one. Now, it might be listed under propellers and wind. I don't know. Okay, here's an axial pump. Oh, well, okay. Okay. I guess that's okay. I'd rather see a centrifugal pump, but that's okay. So the axial pump, the blade, he kind of zooms in on the blade there. And he says the flow into the blade is that. And the flow off the blade is like that. Then he does P exit, P entrance. Okay, so that's fine, but that's still not the one. I'm looking for one that's a centrifugal. Maybe. Yeah, these problems can take a long time if you're not. Okay, come on, propellers. I doubt that this would be, okay, so these other ones are, the red asterisk means most people don't cover them. Okay, well, I don't know about that. That's not exactly what I was looking for. This is what I was looking for. Let me just show you. Let's say you had a turbine, if I can keep talking. So you have a centrifugal pump. You made your blades look like this. Say you had say you had several of them. And so the blade spins around like that. And you've designed your blade so that it comes off like this. So you would have, the design of the blade would tell you this angle. Man. So your velocity of your fluid relative to the steel jacket would be something like, I don't know. Here, let's just call it V magnitude. V magnitude cosine of theta. And you know what? I'm going to make this thing spin this way. So that makes it a minus u theta plus v magnitude sine of theta ur. So you design your blade. That's the one thing you control. If you control this angle, and you obviously want this angle to be the same on every one of these, and you're going to go over to the assumption that the water is going to come off at the same angle all the way across. So you would get this. So if you want to know V, you're just going to take m dot divided by the density in the area, and that's going to be your, so if you want so much m dot to run through your turbine, that's going to be the magnitude of that velocity. Then the fluid coming off is going to be the velocity of the fluid relative to the steel plus the velocity of the steel. That is always going to be omega cross r, or omega r times u theta. And so then you just add this equation to it. Believe it or not, you can work your way through this to find what is the optimal spin rate, omega, to get the most power out of a turbine. Because once you're getting out of this, you're going to get the torque. Okay, so that's what he's getting. If you look back here, he's always finding the torque. Let me go back to this. Let me see. I don't know which one's the best one to pick, but to get your axial pump, you get all done. Now, he may call it moment. He sums the moment, and then he has a T for the torque, but it's okay. Torque and omega are kind of synonymous. So what you're going to end up with on all these equations is you're going to end up with a torque. So then what do? You just figure out your torque times omega, and that's equal to your power. And so what you do is you go through this thing and you're like, so here's what's so interesting. You vary omega and this number changes, right? But you vary the omega and the omega in the velocity equation changing. And so what's funny is there's your velocity in here. So it's not a hard relationship, but you'll find out torque is a function of omega times omega equals to the power. So if you spin your turbine too fast, your water shoots out, and you could reduce your torque. If you spin it too slow, you can reduce your torque as well. So there's an optimum spin rate given, some sort of angle that you have chosen here. So you can design your turbine such that you can get your best torque at a certain speed, your best power at a certain speed. And lo and behold, if you look at those centrifugal equations, you'll find that there's an efficiency curve, and that it goes at a specific speed. And so
you run at a higher RPM, but if you run too high of RPM on the motor, like you're not getting anything out of it, you're just destroying the motor.
right, exactly right. And if you look at it, we'll look at these things later. Let me just do a pump curve. Sorry, I'm coughing up. Here's a perfect one. Not perfect. They all look the same. All of them that have all the numbers in. How can I make that big? Okay. So what you see is these arc curves right here, like the 80. I don't know. I think that says 83.5%, 83, 82. So if you took this particular pump, so whoever designed this pump, I don't know who designed it. It doesn't really matter. It's just a pump. They all have the similar behavior. You come in here and you say, hey, what is the best place to run this pump at? And if you look at it, it's right through here. And the fact that he didn't give anything past this kind of means that's where it should be. So this pump, so these are the different diameters. I think that's 8. I think this is 8.5, 9. So if you want a 9-inch diameter pump, 9.5-inch diameter pump, probably the best place to run it is, I can't really tell, maybe that so many gallons per minute. If you run it too slow, your efficiency drops off quite a bit. So if you ran that too slow, and efficiency dropping off means there's a lot of inefficiencies that are swirling in there. So you can kind of design these pumps, or somebody else can design them, and you can get the pump curve and figure out where you want to operate them. And the best thing to do is look at those efficiency contours and just split them right there. So if you were selecting this pump and you were saying, hey, wait a minute, I need to pump about 600 gallons per minute. Which pump should you buy? If you buy this one, you're gonna be running about 83. If you buy this one, you're gonna be running a little better. So it's probably more efficient to get this pump than that one. And then there are times you might be back here and you're like, oh crap. And then what you do is you go look for another pump, a different model pump, smaller, bigger, different.
Find one that's more range.
Yeah. And so there's an art to picking these pumps, and that's why near the end I cover pump curves and how to go through them.
That's referring to skull head and these are the back stuff.
Yeah, in other words, this thing, well, it'd be either meters or in feet, but this thing could pump up to 70, 80. Well, maybe this, say you bought this one, it could pump up to that high, pump water up that high.
So it can pump it vertically that high?
Yeah. Now, if you're pumping it that high, you might not get. I mean, you get down here, you know. So let's say it's 95 feet. Or, I'm sorry, that's 95. So say it was 95 feet. You turn on that pump, it's just not going to make it up there. Yeah. So then let's say you wanted it 80 feet. So first of all, this pump's not going to get you anywhere, but this one you might be able to get that many gallons up there, given that the pipes are not going to take away a lot of energy. Pipes will take away some of your energy, but so yeah, and we're gonna figure out how to calculate that friction, and then we're gonna figure out also how to pick a pump to fit in this range. And actually, there is I may add this as a lecture in this. I may add it as an online lecture. EPA net. So this code right here is a piece of software, and all you got to do is just download it. It is right here, the self-extracting installation program. So what is cool is it has all of it in there. I could go back one page because the one page, wait a minute. Nope. Okay. Well, I tell you what, this is probably a better place to, let me just click the image. So here's typical examples. Let's see. Well, I can't. Okay. So anyway, you can lay out a whole network. This is like a city thing. So you can lay a whole bunch of pipes out into neighborhoods. And obviously there's a lot of tap points right in here. Whoa, okay. But over in here, there's just pipelines. And over here you have a reservoir, another reservoir, another reservoir, and another reservoir. So you can use this if you wanted to plan out a city, and, say you want to cut off this reservoir for a while. To fix it or something. Well, you need to basically have things come online. Also, it's possible to have support pumps along the way. Although, more often than not, people try to avoid that because if the electricity goes out, your water goes out. But if your electricity goes out, generally your water didn't go out. And the reason being is because there's a big, there's a big tower somewhere with tons of water up there. Now, if the power went off for like a couple weeks, eventually your water, everybody would drain that tank and everybody'd be sitting there with no water. But I may make a couple of lectures on this because this is actually a pretty good piece of software. And given the fact that you just go out there and download it, I used to make people do projects with this where they would do a golf course, and they would have their little lakes in there, and then they would pull the pumps in order to sprinkle. I mean, nobody's drinking any water on the golf course, but you are at night. Hopefully, you turn on the thing and it starts sprinkling your stuff, and then you turn it off. More times than not, you want to use the water that's in those little ponds around there. because that's easy. You just have a pump station, a bunch of PVC pipes laid underground somewhere, and then these little sprinkler heads that pop up and spew water out. And it works really well. This thing works really well on those. Man.
Football stadium that had sprinklers set up on the sides,
Uh-huh.
and they were just long enough to hit the center of the field.
Oh,
And they would run, they would run
in the arc.
180-degree arc.
Oh,
And they would water the whole field out there, and the field was set up out, so it would all come right back to the edges, hit your drain. So whatever runoff you had within like, I don't know, 4 hours, it's pretty well dry.
oh, okay. And they probably were using something like
Somebody
this.
came up with a good idea.
Yeah. So I mean, damn. So tends to work well. You can tell. I mean, look how detailed this stuff is. So I'll go through that, because it's, somebody says they have, somebody had a tutorial. Maybe I don't have to go through it. Hey, pretty cool. Let's see what they have to say. They're probably going to give me
What
an
if there
ad.
was a way to know if a stock will be bullish or bearish the
Who
day
cares?
before? The truth is, there actually is one way. Hey everybody, this is Michael.
Yeah.
Okay, good day, guys.
So let's see the complexity of the problem he's doing. I may just do one in addition. Okay. It looks like
Connects node 1 and node 2.
oh, that's the one that's the example. No, we got to do more than that. So I'll try to make some videos on that. Because inside there, guess what? You do the pump curve. And so you pick your pump. And if your pump isn't good enough, not much water comes out. And then sometimes you can find your pump just won't work. It just won't pump the water out the pipe. Sometimes you'll find that your pump is way too big, and then so you gotta go through the process. Of, the biggest part is laying out the stuff, but then once you lay it out and you have your diameters, then your whole biggest thing is trying to find the right pump, and sometimes that's not as easy as it seems, Oh, if you don't mind, I'm gonna go cough up somewhere.
They don't want you to buy a pump, install it, and it's not working.
Yeah. Some places like Granger, if you go out and look at them, other places do as well. I may misspelled it. I don't know. There's MSC too. MSC.com. Or maybe it's MCS. No, that's not MSC. MCS.com. I don't know. I can't remember. I swore it was. That doesn't look like that's it. I don't know what that is. I'm going to stay away from that. That's the wrong Grangers. Anyway, we'll figure that out later. Excuse me, we still got class period going, but so I'm not sure I am. Thinking about going to Walgreens and getting some medicine or something. So I think if you don't mind, we might just call it a day.